of Unix scale speaking about continuum limits of X.
Thank you for the introduction. Let me turn this on so that I don't run amok. Organizers, I think that's better. I had a bit of trouble in choosing what to talk about given the wide spread of topics that are discussed at this workshop. So what I decided to do was to talk about a topic that sort of lies in between the topics of graph limits and inference and for a different type of problem that we've been seeing here. The graphs I'm going to deal with are all Euclidean graphs. So edges are always defined in terms of some Euclidean distance or Euclidean distance to some power. And so what I hope to cover in the next half hour is this continuum limit machinery. I'm not going to go into any of the details of how it works. The papers are there for that. But that can lead to some alternative ways of looking at limits of random Euclidean graphs in terms of functionals like minimal paths or, as you'll see, other functionals that involve non-dominated sorting and partial orders. And then in addition, it can sometimes lead to new ways of computing minimal paths which have order 1 complexity as opposed to order n squared or polynomial in n, where n is the number of points. So that's what I hope you get out of it. So let's get started. I'll start to talk about just motivating this. What are the minimal graphs and minimal paths that I'm going to be interested in the talk? And then I'm going to talk about some continuum limits, some well-known. And if Michael Steele is here, then yes, hi Mike. Yeah, Mike will recognize some of this. And then we'll go into the continuum limits of the minimal paths and non-dominated sorting that will then finish with an application, if I have time, to an inference problem, an anomaly detection problem. So I really don't have to go over this except for the notation. We're going to define the nodes of the graph as n nodes. They're a set of points in some subset of D of the Euclidean space to the Cartesian product D. So D-dimensional space. The graph is vertices and edges. Of course, edges connect to distinct pairs. We're going to always look at edge length here as defining the strength of an edge, which is defined in terms of a distance metric on this space M. So M has to be endowed with metric space properties in order to do this, at least asymptotically. And then, of course, the adjacency matrix defines those edges that are included in the graph, right? And so we can look at, for example, vertex degree by summing over a row or column of A. These are all undirected graphs, so A is symmetric. And what we're going to be concerned with are certain types of minimal graphs under a constraint which prescribes the domain over which you are looking for constructing a graph from its edges. So we call that constraint set C, and you're minimizing this total power-weighted edge length function or functional LV of E, and it depends on both the vertices and, of course, the edges. So that's the context. We're going to be looking for graphs and minimal paths through graphs and non-dominated sorting types of graphs that satisfy this sort of constrained optimization context. So we all are familiar with k-nearest neighbor graph, which can be described as a solution to this constrained minimization, where the constraint is that the degrees are all greater than or equal to k plus 1, and you construct a forest of graphs with the nearest neighbors of each point, the k nearest neighbors playing the role of the locality that describes the topology of the graph. Of course, these have been used widely in computer vision and machine learning and density estimation. K nearest neighbor densities are related closely to k nearest graphs. Dimensionality reduction and computative complexity is on the order of k n log n. So that's one graph, which is familiar to all of us on Euclidean space. The minimal spanning tree is another one, which is a solution of the optimization of type that every point has to be connected to every other point, and you want to find the minimal graph that spans all of the points. This graph has exactly n-1 edges. There are no cycles. It's not necessarily unique, but it's used in lots of other types of areas in image processing and clustering and so forth. N squared log n is the complexity. So these are two graphs for which there's a continuum limit that goes back to the 50s, which I'll talk about in a minute. But the one that we're going to be looking at, actually two types of graphs we're looking at in particular, is the shortest path graph, and then the non-dominated ranking graph. So the shortest path graph is a graph that is a single path through a topological constraint set, in this case a k nearest neighbor graph with k equals 6, and it has to connect all the points, excuse me, it has to connect a pair of points, x initial and x final, in such a way that, of course, it passes through only those points that are that can have adjacencies, sequential adjacencies along the path prescribed by the graph, and it has to do so with minimal length, right? And so we have this parameter gamma that's going to play a critical role. This parameter is the exponent, the edge exponent. If this is equal to 1, this becomes the standard minimal path length over the plane, and that's of course a straight line, Archimedean axiom going back a couple thousand years. So. But as we'll see, for gamma not equal to 1, in fact, for gamma greater than 1, the shortest path will, in general, not be a straight line through from here to from x initial, x final, even when the graph is a complete graph, right? So we're going to concentrate on that case. So we're going to take this to be the complete graph. So you can take any path. Any pair of points are adjacent, and we will see what goes on with this. But first, let's just recall that these shortest paths are used in machine learning with Isomach geodesic approximations using Dijkstra's algorithm to connect a path through the k nearest neighbor graph, for example. They're also been used in computer vision and database indexing and retrieval, finding shortest paths through consumer goods so that one can find a continuous morphing through the database relative to a path that connects these two different types of boots. And that shortest path is a path which is relative to some distance. In this case, the distance measure is the Kullback-Leibler distance between the SIFT features. So SIFT features are a kind of spherically invariant feature transform set that is defined for images and extracts the salient points of each one of these images and then tries to match them using a histogram matching type of technique using Kullback-Leibler, symmetrized Kullback-Leibler distance. And an important thing about this is that as the database gets denser and denser, and that's the sense of continuum limit that we're going to look at. So let's say there are lots and lots of shoes in this database. As it gets really dense, the distance measure that's being used to trace out this path is actually superlinear in the Euclidean distance between the SIFT features, right? Kullback-Leibler distance is quadratic, right? For close featured distributions, for two distributions that are close, it expands out in terms of the first significant power in the power expansion is the square, right? With a Fisher information deformation metric, right, on the Euclidean distance squared. So that's going to correspond to a gamma not equal to 1. So we should expect that in this case, the straight line path is not going to be the shortest path from here to there, that it's going to have to travel through some other region. So also used in epidemiology for virus strain genotyping and looking at centrality, shortest path centrality, or betweenness as it's called, for identifying the etiology of different viral mutations, in this case influenza A. So this is shortest path is a very ubiquitous thing to look for when you have a Euclidean length definition of your edge weight. So gamma is equal to 1, and here I'm denoting a Gaussian set of points. The shortest path is always just the straight line path, the Archimedean solution. When you have a distribution that has concentration, like here is a Gaussian distribution, and instead of the length, it's the length squared for gamma equals 2, now the shortest path is deformed. And this is what some people like to call the lensing effect, just like in general relativity, right, where you have a very high density of points, it tends to attract minimal paths towards that point of high density. And why this is happening is simply because if the distance is superlinear between points, then there's an advantage to pass through dense regions, right? Dense regions of the data. And of course, if you're uniform, there are no dense regions. So even with Euclidean distance squared, you get approximations to this straight line path. And indeed, what we're going to show is that in the continuum limit, as we take the number of points going to infinity, that this sort of jagged approximation indeed does converge to that straight line in the uniform case. And in the non-uniform case, we get a characterization of this curve, right, as a function of the underlying density function. So that's the first problem that I'm going to discuss, the first continuum limit. And the second continuum limit is another type of shortest path, but in this case, it's the non-dominated ranking problem. So here are our points, our n points, again in Euclidean space, and we're going to define a partial order relation if between x and y, two vectors in this d-dimensional space, that x is dominated by y if it's dominated in every element, right? All d elements. And so you can define a minimal element that basically says that that is minimal if it's not dominated by any other elements, and that's not unique. And so that's going to lie on what was called a non-dominated front, or a Pareto front in multi-objective optimization. So the minimal elements of this set are all the points down here which basically are not dominated by any other point, right? You get better as you go towards the origin here. So we're talking about domination in terms of being small, right, in both coordinates. And then you can peel away these Pareto fronts one by one and discover, different sets of these what are called anti-chains for the data set of interest. And so these Pareto analysis or non-dominated ranking analysis arise in lots of areas, including one interesting area, portfolio design, which I only discovered recently, where the high rollers go into their banker and the banker presents them Pareto fronts in terms of risk and return of given stock options, right? And then they fill their portfolio according to whether they're more sensitive to risk or more sensitive to return, right? And so these are highly used. Computational complexity is order n squared. So an illustration of this, which is kind of cute, is when you're trying to do image retrieval, but you want to combine different semantic concepts. So let's say you and your partner are going to go on vacation, and you like the seaside, you like the water, you like to swim. Your partner prefers to go hiking in the mountains and likes the fresh air and so forth. So you and your partner have these two photographs of your favorite places to go. And you want to find a place that sort of combines them both. So this semantic concept is water, this semantic concept is mountain, and so this is your desired match here. So the standard imaging match that you get in Google Images, for example, is limited because it only produces one ordered list, right? And the desired match may be, for all intents and purposes, infinitely down in the index of your ordered list. And most people only examine a few of the top matches. So you end up, I just actually put this into Google Images. So the first 8 matches, there are no mountains here, and there's no water in this case. So if you get tired after looking at 8 matches or maybe 800 matches, you're not going to find the combined multiple semantic concept. So a solution to this is to use Pareto fronts, right? So in the Pareto fronts, what you do is you look at, instead of just a single ranking represented by 2 lists, and then trying to merge them at some low point on the index set, instead you go and find these Pareto fronts relative to being attractive in terms of the beach or the water, and attractive in terms of the mountain. And then what you'll get, and this is an actual example from the Stanford scene data set that we ran and reported in this paper on recently appeared in Image Processing Transactions. And so what you get are these red fronts, which are the first 4 fronts that cover about 100 points. There are about 100 different solutions, if you like, and you and your partner would probably look right in here, right, at a good combination of your 2 concepts. If you were to use scalarization, what does scalarization mean? It means I'll take a linear combination of the distance matching that comes back for my partner's image in the database and my image in the database. You take that linear combination with some lambda, let's take it 1/2, so you don't want to fight with your partner, so you give each one equal weight. Then what you'll be doing is you'll be ranking in terms of these diagonal lines, right? And as you dig through the database, you're going to pick up successively these points on the edges, and in order to find yourself in this sweet spot here, you're going to need order of magnitude more points on the list to look at in order to come to it. So this is because the Pareto fronts are non-convex, right, in this case. And that's where the interest of using this Pareto matching occurs. The other nice thing you can do is you can sort of peruse this sort of morphing, as I had mentioned before, in the context of the shortest path from, in this case, I guess we're looking at forest versus mountain from, along the front as you index over the front from highly close to the query on forest to highly close to the query on the mountain. All right, so those are 2 types of graphs. One's actually a single path. The other ones are sets of paths. And so now we're going to talk about continuum limits. So the first continuum limit that we've known for many years is for the minimal spanning tree, or the k-nearest neighbor graph, where we notice that if you take the minimal spanning tree, in this case over a uniform set of points, and the minimal spanning tree over some concentrated set of points from IID from an underlying distribution, that you get a total length which is larger for the uniform set of points than the smaller set, than the more concentrated set, and that's effectively encapsulates the fact that the minimal spanning tree is sort of capturing the the spread, right, of the distribution, the underlying spread or entropy of the distribution. And if you plot then the length of the minimal spanning tree as a function of the number of points that you include in the graph, then you see that you get this sublinear increase in the length. The length is increasing in the number of points that you add, and there's a larger slope, if you like, for the uniform than the triangle distribution because of this concentration property. And if you take the log of the length and divide by root n in this case, you converge to a limit. And that is the celebrated Beardwood-Halton-Hammersley theorem, which is beautifully laid out in Mike Steele's SIAM monograph on probability theory and combinatorial optimization. And this gives us our first continuum limit. As you take the limit as the number of points goes to infinity of any quasi-additive continuous functional, but it means the minimal spanning tree and the k-nearest neighbor graph in particular, it converges if you normalize it by the right constant, by the right function of n raised to a power dimension minus this gamma parameter divided by dimension. It converges to this function here of the underlying density, which, if you take the log of this and divide by 1 minus alpha, this exponent, this is what is known as the Rényi entropy in information theory. And so this gives you a way, if you like, to estimate entropy using minimal spanning trees or k-nearest neighbor graphs. Performing inference, this is almost sure convergence. You can also get bounds on the rate of convergence, and there are central limit theorems and so forth, so you can develop a full inference of entropy using these types of minimal spanning tree k-nearest neighbor graphs. So I can't spend time going through how this continuum limit comes about. I had a slide on that, but because of my my limited time, I'm just going to skip that and show you a theorem, sort of a corresponding theorem that generalizes this Beardwood-Halton-Hammersley to the case of the shortest path. So it looks kind of strange, right? So it's a bit harder to interpret, but here I go. So what we're going to assume is that there's the marginal probability distribution f, that is the joint distribution of the xi's, has some support set S. We're going to assume it's compact. Actually, this holds even if it's simply closed, but I'll assume it's a compact. And then you fix these 2 points. And if you assume that the support set of the density lies on some nice, smooth, regular surface, like a Riemannian manifold with a positive definite metric tensor G, so an inner product of the metric tensors and then in this case for gamma greater than 1, the shortest path between the 2 points will, if it's suitably normalized by n to the power 1 minus gamma over d, converge to this limit. Okay, so this is a limit which involves a path, that's pi. So pi is any path that goes through the complete graph. And the pi that wins, the one that minimizes the total length, is the one that minimizes this integral. And here we parameterize the path with its parameterization from 0 to 1 over domain. So pi is obviously in d dimensions. And so it looks like we have a weighting of the metric that describes the natural curvature that determines the distance between points in this space S. And this is a well-defined distance measure between the initial point and the final point, but look, it depends on the density. So when you look at this minimization, what you see is that indeed we have this kind of inverse weighting in the density, because here gamma is greater than 1. So this is a negative exponent, right? So what we're saying is that the path is going to tend to prefer to pass through regions which are highly dense. And so we get this, this characterization, but now through a smooth curve because we're in the continuum limit as n goes to infinity.
Excuse me.
Yeah. Positive definite. It's just a positive definite metric tensor. It's just a, it means that the curvature is well defined. Yeah. And so this just, so the main ideas behind the proof, I'm not going to go through it because I only have 2 or 3 minutes left, but there is a paper on this. We can distill the steps in the paper down to an argument which is similar to arguments used in Beardwood, Holt, and Hammersley proofs, the partitioning or dissection of the points, and then you make a, just to simplify things, you just make the intuitive assumption that the average interpoint distance is going to be the 1 over the dth root of n in a d-dimensional space between any 2 points. The average number of points in a short path is going to be on the order of the dth root of n, right? Because it's a one-dimensional trajectory in a d-dimensional space. And then it's very simple to look at, what would be the average path length. It's simply the number of nodes on the path, along the path, times the average length, and that gives you this exponent, right, that we were looking at before. And then to bring the density in, you have to do this sort of partitioning to bring in the subadditivity property. And I'm not going to bother dwelling on that. What is, I think, the most salient thing here is we have a variational interpretation of this result. And what do I mean by that? There's a differential equation that is the solution, that describes the solution of this variational problem. We're trying to minimize this functional subject to the constraint that the initial point is equal to xi and the final point is equal to xf. So this turns into simple calculus of variations on that integral. You can show that that the shortest path has to satisfy a system of decoupled Euler-Lagrange partial differential equations. So here are the partial differential equations given here. This is a gradient with respect to the derivative of the path, the derivative with respect to the parameter t that parameterizes the curve. And this is a derivative with respect to the path itself. And f pi dot is the integrand. And if you specialize to the case where you're in a Euclidean space, there's no, this Riemannian tensor is just the standard inner product. Then everything boils down to this equation, which very compactly encapsulates the what's going on, especially if you go down to d equals 2, the plane. Now I can parameterize my curve by t, the parameter, domain parameter, indexing the curve, and then y of t. So over the plane, I just have t, y of t, and we go through the plane over some curvilinear in the case of, or piecewise linear in the case of finite n. And then you get a specialization of this PDE to one equation, also a partial differential equation. But you can see if gamma is equal to 1, then this disappears, or if the gradient of f, if f is uniform, f subscript 1, 0, and 0, 1 is simply the gradients or the derivatives of the first and second argument, respectively, of the density. If that's constant, that's equal to 0. So if this is equal to 0, what this says is that the derivative of that curve has to be equal to 0, which means the curve has to be constant, so it's a straight line, right? So we get a straight line in the special case of gamma equals 1, where all of the points are nearest neighbors, and the distance between those points is minimal over any path, or when we have a uniform distribution. And this just shows that you can that this is validated. All right, so that's the first continuum limit. Yeah.
I'm a little surprised that the parameterization matters. I mean,
it doesn't matter,
of course,
right?
But
Yeah, it doesn't.
Didn't you get an ODE in that case?
Oops. So no, it's well, you look at at this case, it's a partial differential equation because you have a derivative with respect to t and respect to y. Right. Right, because f is a function of two variables, right? So it would be an ODE if f was uniform, right? If f was uniform, then you'd only have this ODE here, right?
Again, you're just going to draw a curve. You don't really care. I mean, given
Right.
the curve and the density, you'll be able to reconstruct the parameterization from it. So you should be able to reduce this further to an ODE. That's what I'm saying.
Perhaps. Okay, we should talk afterwards to see. Yeah, that would be even better. Right. So good. Thanks for that comment. The point here is that we have a PDE that we can solve on a fixed grid, if you do a numerical approximation, which is order 1, right, relative to the number of points. As long as you can get an accurate estimate of the density, note it's the density that drives this PDE through the log likelihood function, or the gradient of the log likelihood function. So we have an order 1 approximation to an order n squared problem, or to be more honest, if it's order n to estimate your density, it's an order n approximation. So this is a continuum limit for the dominated sorting problem. So this is just a demonstration for a uniform distribution. Here are some selected Pareto fronts. I think maybe every 20 Pareto fronts is denoted here in terms of these two criteria on the plane and the uniform distribution. As we take more and more points, we seem to converge towards some continuum, right, of the Pareto front. So these curves seem to become smoother and smoother, suggesting there might be a PDE for these curves too, right? Or maybe an ODE. And if you insert a box to null out part of the distribution, we get a similar type of convergence, except that you can see that there's a sort of shock phenomena that occurs at this discontinuity where that box presents a discontinuity in its circumference. So we have an asymptotic theorem for this, and this theorem says basically that if you define this function that counts the number of Pareto fronts in a wedge, so you're looking at a simple wedge that if you have all your points, and these are your two criteria plane, then you look at this wedge region, and that's the only region you have to look at in order to establish dominance that for the purpose of the partial ordering. So this U of n counts the number of Pareto fronts in a wedge, and if you assume that the support is bounded and the boundary is Lipschitz, so we need a little more conditions here, then you get this theorem that says that this function that counts the number of Pareto fronts, which you can look at its derivative is sort of the Pareto index, the Pareto front index of a particular location in the plane, right? That converges to this, another variational problem when you normalize by 1 over the dth root of n. And this also involves this gamma prime, or again, the derivatives relative to the parameterization of the curve. And you have the dth root of f, the underlying density function evaluated at each point along the curve. And there exists a PDE that describes this variational problem, which is the Hamilton-Jacobi PDE, actually previously unknown in the applied math field, according to my collaborator, Selim Ezadoglu in the math department of Michigan. He was quite excited when he saw this because he'd never seen a Hamilton-Jacobi PDE of this type. And so this led to a lot of sort of theoretical work in finding numerical approximations to this. And then this is just a demonstration that shows how close the theory is to the actual Pareto fronts. You get this shock, which is well known in the applied math PDE world for this Hamilton-Jacobi class. And as I said in the beginning, this is related to the longest chain problem, which was studied by many people, including David Aldous, I believe. and Stan Ulam, and I won't bother saying any more than Pareto fronts are simply anti-chains to relative to chains of non-dominated points. Yes, and I'm almost at my last thing. You can effectively formulate a numerical PDE solver that we recently published in SIAM Numerical Analysis. We applied this to anomaly detection. I'm not going to describe this application because I don't have time, but suffice it to say that we're looking to classify curves and find anomalous curves in the trajectories of people as they go out on their lunch break into an atrium and either walk around aimlessly or go to a restaurant or what have you. So the problem here is intrinsically difficult because there's really no single criterion that you can use for these curves because there's speed along these curves. These people are walking at different rates, and there's shape. So these are two separate criteria, meaning that if you want to detect anomalies, you have to use them both. So what we do is we apply our non-dominated Pareto analysis to detect those anomalies by looking at basically how deep the Pareto front is that contains any one of these curves. The deeper the Pareto front, the less it dominates the others, and so therefore the more anomalous. Right? So that, in a nutshell, is what we do. And the important thing here is this curve, these curves, which show the order 1 PDE solver CPU time complexity, computational complexity as the number of samples increases. Here, we have on the order of a billion Pareto points because we're looking at all pairs of points in this particular case for computing that distance between trajectories relative to those two criteria, right, speed and shape. And so you get a significant computational advantage by using a PDE solver as opposed to actually computing the Pareto fronts, which is, as I say, an order dn squared operation. So just to summarize, we've I hope convinced you that there's some interesting connections here with the science and mathematics of PDEs for these shortest path types of problems. I've just shown you 2 examples. I think there are many more in which you can find these relations to PDEs. And this is what really excites me about this type of work is that the applied math, computational physics community, and the the more pure math community, graph theory, and so forth, haven't really talked to each other a lot. And it's with these types of connections that perhaps that things can be improved. And this is just a very minor step in that direction. But there are lots of cool open problems. Hi, Steve. Everyone can say hi to Steve. And minimal paths over directed graphs or sparse graphs. These are over dense graphs, right? The complete graph is the densest graph you can get. So those minimal paths are over the dense graphs specified by the complete graph. Hypergraphs, multigraphs, non-dominant sorting extensions that handle things like Tukey's data depth, peeling the onion to determine depth of points in a point cloud, or convex hull peeling. Actually, I don't think that problem's open anymore. Jeff Calder just solved it, and he submitted a paper recently on this. Yeah, so this is just my collaborators. Yeah. Yes.
Yeah, so go back to the shortest path problem. You found a nice characterization of the limiting path. So have you studied the fluctuations, about the rate of convergence to it, and whether fluctuations are Gaussian, so to go even further?
Yeah, we don't have any distributional weak convergence results. We do have, I can tell you that we have results that are, this is sort of the weakest form of the results we have in our paper, which appeared in the Annals of Applied Probability this year, in the sense that we do have bounds on the rate of convergence, this almost sure convergence, right? And those are exponential concentration type bounds. But we don't certainly have any central limit theorems or other types of limiting, weak law results, which would be great. But we don't have those. We haven't even started considering that problem. Thank you. Yes?
This is a strong law for IID observations, so the extreme context for that would be an ergodic type theorem.
Yeah.
It turns out that the corresponding ergodic theorem for the Beerwood-Halton-Hammersley theorem is not true. Although there are some other things that don't seem so different from Beerwood-Halton-Hammersley for which it is true. So
Interesting. Yeah.
Interesting to know in this case that it worked in the
ergodic case.
ergodic case.
Yeah, that's very. It's a good question. I can't, sitting up here, go through the proof and see just where the IID case might be, weakened to exchangeability or ergodicity or something like that. But it's scary if the BHH theorem doesn't hold in that case.
Well, you can construct a sequence of you construct a stationary sequence which ends up at more and more remote scales has too many twin cities, and that can bring down the BHH constant. But having an excess of twin cities wouldn't interfere with that result.
Right. Yeah.
So
yeah. So maybe there's
an own example wouldn't contradict this for an ergodic case.
Mm-hmm. Yeah. Thanks. That's interesting.
Any more questions? Maybe the last one.
The last result on the Pareto fronts, I think, was that just in two-dimensional data?
No, that's general for D dimensions. Yes. Yeah. Yeah. We show it in 2 dimensions. Now, we have to be careful.
Increasing sequences, basic sort of 2-dimensional.
Excuse me?
You said you were using results about the length of the longest increasing sequence.
Right. Yes.
Sort of 2-dimensional, this is.
Well, we use that's an analogy that we're using. Yeah. In the actual paper, we make the analogy, but then we have to use our own machinery in order to push this through. But it is a good point about D, because if D is greater than 3 or 4, there are no sort of off-the-shelf numerical algorithms for solving PDEs of high dimension that we know of. So in terms of practical implementation, D has to be relatively small. The theory works for any D, but to be able to actually implement these PDE solutions numerically, D has to be manageable. Yeah.
Fine. So that's fine.
Thank you.